Go.
All right, so today's PowerPoint is going to be on transistors and LEDs. We're going to go over the history, applications, and some physics equations that are part of it, okay? So the history of transistors, before transistor vacuum tubes were used in early electronics to amplify signals and switch signals. However, they were bulky, fragile, power hungry, and produced a lot of heat. In 1947, scientists John Bardeen, Walter Brayton, and William Shockley at Bell Labs created the first working transistor. It was a point contact transistor made out of germanium. This breakthrough replaced vacuum tubes with something smaller, faster, and more reliable. In 1948, William Shockley created a more practical transistor, the bipolar junction transistor. This became widely used. This one right here. In 1959, Muhammad Allah and Dawin Khan at Bell Labs created the metal oxide semiconductor field effect transistor, the MOSFET. In 1960s, today, transistors were combined into integrated circuits leading to microprocessors, modern computers, smartphones, and digital devices. Today, billions of transistors can fit on a single chip, enabling digital age. Transistors are arguably the most important invention of the 20th century. So transistors are made of semiconductors. Transistors are primarily made of silicon doped with other elements like boron, which is a p-type semiconductor, and phosphorus, which is an n-type semiconductor. Silicon crystals at room temperature have sufficient heat, thermal energy, for some valence electrons to jump the band gap from the valence band to the conduction band. These electrons are called free electrons or conduction electrons. This creates a vacancy in the valence band. So something that you can see is it creates like a hole once it jumps. So with the semiconductors of a p-type semiconductor and n-type semiconductor, practically you're just doping them with an impurity. So adding an impurity like boron with 3 valence electrons, replacing a silicon atom, it accepts an electron, has a hole, creating a p-type semiconductor. Adding an impurity like phosphorus with 5 valence electrons, replacing a silicon atom, it donates an extra electron, it has a free electron just roaming around, creating an n-type semiconductor. Any questions? No? So I don't know if you guys took, when you took chemistry, anybody else, they went over this over one-on-one at the very end. So when you smash both of these together and create a transistor, you create a p-n junction. So normally you'll have your p-type semiconductor and your n-type semiconductor. So you have an excess of electrons or free electrons, and then you have the holes. Naturally, they're gonna want to jump over to the p-type semiconductor. So there's like a Coulombic attraction. Once that happens, it's slightly negatively charged on one end and slightly positively charged on the other. This creates the p-n junction. Then there's an electric field that happens. There's an electric field that forms, and it stops the free valence electrons to jump over this p-n junction. This region is called the depletion region. There's a potential difference of 0.7 volts. So when you add voltage, anything higher than 0.7 volts, the depletion region gets narrow or collapses, and then electrons start to flow. That's pretty much the premise behind this. There is 2 different types of p-n junctions. There's a forward bias, which the depletion region collapses, like we were saying, with voltage supply, and electrons flow. If you were to reverse the polarity on the battery, switch it around, it creates a reverse bias, and pretty much the electrons attract to each end, and then the depletion region increases. So this is where kind of transistors, the more common one is the NPN transistor, is when you have, the n-type semiconductor, the p-type semiconductor, and the n-type semiconductor. So practically the same thing happens here. We have the emitter pin I'll show you guys that in a little bit. This side's heavily doped. The P-type semiconductor is lightly doped, and the N-type semiconductor on the right is moderately doped. When we apply voltage to one of the emitter and the base pin, the depletion region collapses and electrons start to flow. I know you're asking now is what happens to the reverse bias here. When we apply voltage here, there's like a Coulombic attraction, and also I want to say the best way I can give it is electrons start to push on each other, and they jump the gap over the depletion region. Once you apply more voltage, any higher voltage, 0.7 volts, the transistor fully opens and electrons start to flow. So you'll see kind of like a logic gate. So the other way I can explain transistors, if you're still not getting it, is you can imagine we have water in a pipe, and we add 2 discs on each region, and a pulley system. If we were to apply a little bit of water on one of the swing gates, nothing happens. But if we apply the minimum required to open the gate, in this instance it would be at 0.7 volts, we can see that the water flowing in from the main pipe gradually opens. Once we add the maximum flow on this pipe, it completely opens the water flow. This is the best analogy I can give you for a transistor. So practically what a transistor is it can be an on and off switch, it can be an amplifier. That's why they're so useful. It's non-moving parts. If you were to use something similar like this, it would be like a relay, and it uses a mechanical swing arm to pass voltage through 2 points. This has no moving parts, so you can see how these would last a long time. So some equations that they use for transistors are Kirchhoff's law. I'm pretty sure you guys seen this in physics. It's the current coming in from the emitter pin equals the current coming in from the base plus the collector pin. Some other stuff is current gain equations is common emitter current gain, beta. This practically is just an equation to give you a ratio. It has no values on it. It just tells you like, hey, if I have 25 milliamps coming in from the emitter, or the emitter, or the collector, one of the two, and we have 1 or 2 milliamps at the base pin, it'll just give you a ratio. So like if it's 2 for the base pin and 25 milliamps, I think it'll be like 12.5 milliamps per 1 milliamp that you'll be able to control. So that's pretty much it. Edwards mole model is pretty much an equation that tells you how delicate it is to make adjustments at the base pin, and you can make an adjustment and it changes the equation exponentially. So we have the collector current equals the saturation current times an exponential function of VBE, which is the base emitter voltage, over the thermal voltage, is just the room temp. So let's say the base emitter, the base pin, you add more voltage to it. You can see how the equation moves exponentially. So the bottom will say this exponentiation explains why the BJT, NPN, and PNP transistors is so sensitive to small changes in the base emitter. Let's see. Some applications for transistors, like I said, it acts like an on and off switch, controlling the flow of the current, digital logic circuits, and or NOT gates, microprocessors, microcontrollers. It has billions of transistors. Relay replacements in solid state electronics. That's how I was saying you can replace relays, power management, turning LEDs or motors on and off. So this will kind of tell us into LEDs, how LEDs work. So some history about LEDs is in 1907, English engineer H.J. Round at McCurney Labs discovered electroluminescence in silicon carbide while experimenting with diodes. LED saw a faint light, but it was understood or practical at the time. This is him right here. In 1927, the first LED concept, Russian-Soviet scientist Oleg Losev discovered and documented LED effect. He published a paper on it, but it was ignored for decades due to the lack of practical use. That's this guy right here. In 1962, American engineer Nick Polonyak Jr. at General Electric invented the first visible spectrum LED red light. He is often called the father of the LED. That's homeboy right here. In 1970s, more colors were developed: green, yellow, orange LEDs. Still not very bright or efficient, but useful in indicator lights and digital displays. You can see them like, I think the best ones are like in old cars, you know, got digital displays, like bright green lights. It's very nostalgic. CD players, stuff like that. In the 1990s, the blue LED breakthrough. Shuji Nakamura developed the first high brightness blue LED with gallium nitride. This allowed white LEDs by combining red, green, and blue, or using phosphor. From the 2000s to now, LED revolution, LEDs became brighter, cheaper, and more efficient, widely used in lighting, TVs, phone screens, signs, car, headlights, and more. So that's a brief history. So how do LEDs work? So LED stands for light emitting diode. It's just two semiconductor materials, P-type layer and an N-type layer. Electrons jump from both semiconductors from one layer to another, and as they make the jump, they emit a photon. So that's how we get the light, right? Different materials produce shorter or longer proton waves. The length of the wave determines the color of the light produced. The color is not determined because of the case, so that's a common misconception. You know, how they have red LEDs, there'll be a red casing. It's actually not that, it's the light wave. Blue LEDs were the hardest color to create, actually. That's why it took so long. Some equations for LEDs. I think everybody here knows the energy emitted from a photon. E equals hc over lambda. It's very common in physics and chemistry. I think the band gap is the same thing. This one equation is used for everything. If you're using EV instead of some other form of energy, the basis is 1240 EVs per nanometer. This is how color and wavelength of the LEDs is determined. Pretty sure everybody knows the lambda equation. So determining the color, semiconductor material matters. So here we have a table that kind of says it, because each material has a characteristic band gap energy that directly controls the photon energy. So for gallium arsenide, it's about 1.4 EVs for the band gap. It's infrared. Gallium phosphide is about 2.2. This creates green/red. Gallium nitride is 3.4, and it's blue/violet. I messed up right here, but it's Indian gallium nitride. It's 2.5 to 3.4. Green. This creates green or blue. Aluminum gallium indium phosphide is 1.9 to 2.2 electron volts. This produces a red-yellow. So an example of this, if we're trying to figure out what color it's going to be based off of the material, we already said that E is 1240 electron volts per nanometer. That is just a constant. And if we're using gallium nitride, it's 3.2 EV. If we do the equations, about 388 nanometers. It's about violet or UV light. Some applications for this is general lighting in homes, street vehicles, displays on phones, TVs, indicators, electronics and appliances, signaling, traffic lights, infrared remotes like TV remotes. We can use in industrial medical applications like sterilization, phototherapy, something like this, or something like that, phototherapy for a baby. So that's pretty much it. Any questions? Awesome.
Thanks. Thank you.